This is a pretty cool lesson. So this is going to be, without a doubt, the most interesting part of the course. I'm fairly confident you'll find it the most the most interesting. Not that the other material wasn't interesting as well. This is probably in a lot of respects the most interesting part of physics, the material that we've covered. It's the hardest for this section. It's not the hardest in general, but it's the hardest for this series probably. But it is the most interesting. Okay, so we've done all of these. We've done all these electromagnetism equations, Maxwell's equations for electromagnetism, and we said at the end that it gives you light. That light is the end product. But how does that work out exactly? What's going on here? Well, we're going to treat light as a classical field. I want to emphasize something about light. When we talk about light today, we're talking about certain aspects of light. Just like in the displacement current, the reason we could pretend that it's an actual current is because in that equation, the Ampere's law isn't looking at every aspect of charge. It's looking at the electric field aspect of charge. So it's an equation describing the behavior essentially of the electric field component of the charge. The charge has other components like mass and things that we're not worried about. Today, for light, we're going to be worried about aspects of light such as its energy, its momentum, and its propagation in space when it's behaving like a classical field with a continuous wave, a continuous disturbance that's represented by an alternating electric and magnetic field. Now, the amazing reality of physics, one of the things that continues to make physics unsolved today completely, is that light does also have another nature that's not continuous, that's discrete. It comes in quantized bits called photons. When you get to the extremely small numbers of photons, you have a very different behavior where it doesn't always behave like a wave. It sometimes behaves like a particle. And there's other aspects of light that oh, sir, can you please move down to this row? Yeah, he's yeah, thank you. So there's other aspects of light that we're not going to deal with today, but I just want to stress that there's more to light than what we're talking about today, but today is a pretty good first image of it. The other aspects of light are things like it does have a spin to it. It has a spin polarization. Actually, when it goes through and does something like diffracts, it actually diffracts with a probability. It's not a definitive law that's based off of just like it's guaranteed to go through. It's like if a polarizer has like an orientation at some angle, it might be 50% chance it goes through and 50% chance it doesn't. And determining whether or not it goes through, it can't be determined absolutely. It's just like rolling a dice, which is what Einstein had problems with. And a lot of other physicists had problems with. They felt like we had incomplete information about it. Maybe we do. That's still an unsettled problem in quantum optics. But anyway, in summary, we're going to go over a very interesting aspect of light when it behaves like a classical field. So we have Maxwell's equations and electromagnetic waves. We've studied the aspects of electric and magnetic fields, and we learned that the fields don't vary with time, such as electric fields produced by charges at rest or the magnetic field. We can analyze the electric and magnetic fields independently without considering interactions between them when they don't. But when the fields vary with time, we have things like Faraday's law. And then we can't really have a magnetic field without considering an electric field as well. So Faraday's law tells us that a time-varying magnetic field acts as a source of electric field. And we'll see that that's also true on the opposite end of it as well. So a time-varying electric field acts as a magnetic field, which you could already see, right? Because when you have current going, current has electric field associated with it. If the charge is moving, the position of that electric field that's coming from the charge is changing with time, and that produces a magnetic field. We had that from the beginning, so we can see how they both are duals of each other. Okay, so Faraday's law tells us that a time-varying magnetic field acts as a source of electric field, as shown by induced EMFs in inductors and transformers. Ampere's law, including displacement current, shows that a time-varying electric field acts as a source of magnetic field. This mutual interaction between the two fields is summarized in Maxwell's equations, which we talked about last chapter. Thus, when either an electric or a magnetic field is changing with time, a field of the other kind is induced in adjacent regions of space. So we're talking about how these fields change in their spatial orientation. When one's changing, another one changes in response to that. And eventually, if we get to it, what we'll see is that electric and magnetic fields are actually one unified field called the electromagnetic field. That's the unification, the full unification of electricity and magnetism completed when you consider the Lorentz transformations, which is what Einstein did with special relativity, being an extension of that unification. So we're led to consider the possibility of an electromagnetic disturbance consisting of time-varying electric and magnetic fields that can propagate through space from one region to another, even when there's no matter in the intervening region, such as a vacuum. So we're looking at places in space where we have open regions where there isn't a source of charge, but there's still fields traveling through those regions. And when we solve Maxwell's equations in those regions, that's when we get light propagating through vacuums. These waves do exist. These are the radio and television waves that we get for so many of our transmissions and our useful communication devices. Satellites, telescopes receive light, and satellites communicate light using light. All sorts of different ways that we can get this light to us. Okay, so we're going to see how these waves are explained by principles of electromagnetism. So the theoretical understanding has evolved in a long way, and I'm not going to go into too much detail about this historical stuff, but there's a ratio of velocity and to the measurements, and they found out that basically light is always going at the same speed. For a while they thought that there was an ether and that light needed something to travel through, because like a water wave travels through the water itself. So how can you have a wave without a medium to transport it? Well, they thought there was one called the ether, but it turns out that it doesn't exist. It's just that that's the way that the fields behave. They behave like a wave without needing a medium. That's a postulate that Einstein took. And so the speed of light is always the same, constant in a vacuum, no matter what. So, in searching to understand this result, Maxwell proved in 1865 that an electromagnetic disturbance should propagate in free space with a speed equal to that of light, and he showed that the light waves were likely to be electromagnetic. So at the same time, he discovered that the basic principles of electromagnetism can be expressed in terms of Maxwell's equations. These four equations are Gauss's law for electric fields, Gauss's law for magnetic fields, showing the absence of magnetic monopoles, and then, which we talked about before, that the question like that was on your first exam, Faraday's law and Ampere's law. So there's Faraday's law and there's Ampere's law. We've seen all of these now with displacement current as well. Okay, so these equations apply to electric and magnetic fields in a vacuum as well. If a material is present, the electric constant and magnetic constant are replaced by those for the material. And if they're different at different points in the regions, then these become integrals, and you have to place them inside the integrals because then they become functions. We never dealt with any situation that complicated, but that is possible in different situations. Okay, according to Maxwell's equations, a point charge at rest produces a static E field but no B field, whereas a point charge moving with a constant velocity produces both E and B fields. Maxwell's equations can also be used to show that in order for a point charge to produce electromagnetic waves, the charge must accelerate. So we're going to have a situation where we have this nice sort of process. We have a charge that's moving, that's not moving. What's it produce? An electric field. We have a charge that's moving at a constant velocity. What's it produce? An electric field and a magnetic field. We have a charge that's moving, but then it's accelerating. What field does it produce? It produces three types of fields. It produces the electric field from its static charge. It produces the magnetic field, and then it's an acceleration, so it's producing a light field too. So the acceleration of a charge produces light. Yes, question. Yes. Yes, acceleration or deceleration are the same like the process is a little different, like whether the way things go, but yes, there's also a form of radiation called braking radiation, Bremsstrahlung. So yes, when you decelerate a charged particle in like a particle accelerator, you will also get radiation emitted. Correct. It's not just acceleration in a positive sense, deceleration as well. Any type of acceleration. And not just acceleration in a linear sense either. If you do a form of angular acceleration where you have a charge that's changing its angle, even going at a constant speed but changing its angle, that's a form of acceleration as well. That produces a different type of radiation associated with it. Neutron stars, pulsars, when they rotate, they produce high energy beams of radiation shooting out in specific directions because of their angular acceleration of the charged for different things like that. So anyway, that's the pulsar, the example of that too. It doesn't necessarily just have a, it doesn't just apply to linear acceleration. Okay, so in every situation where electromagnetic energy is radiated, the source is accelerated charges. So we're always having an accelerated charge that's doing that. So one way in which a point charge can be made to emit electromagnetic waves is by making it oscillate in simple harmonic motion. So we're going to have these AC circuit simple harmonic motion type equations. And yes, AC circuits can be used to generate light. You'll see that. So that basically it has an acceleration at every instant. And the exception is when the charge is passing through its equilibrium position. So we'll see in a second some of the electric field lines produced by an oscillating point charge. The field lines are not material objects, but you may nonetheless find it helpful to think of them as behaving somewhat like strings that extend from the point charge off to infinity. The oscillating charge up and down makes waves propagate outward from the charge along these strings. So this is an important device for understanding what we're talking about here. We're considering the field lines as sort of strings, okay? It's not string theory, but it's, getting there a little bit. So, the charge does not emit waves equally in all directions. The waves are strongest at 90 degrees to the axis of motion of the charge, while there's no waves along the axis. This is what the string picture would lead you to conclude. There is also a magnetic disturbance that spreads outward from the charge, and it's not shown because the electric and magnetic disturbances spread or radiate away from the source. So the name of the electromagnetic radiation is used interchangeably with waves. So here's a picture of what we're talking about. We have this charge. This is at time equals 0. Then at a later time, we have the disturbance is changing, okay? And we have this sort of process where the field lines produce a sort of pinching, and it produces it's really hard to really explain how this gives light. So I'm going to have to talk a little bit more about this. But what you can see here, what they're trying to express that's hard to see in this picture, is that there's like a kink in the E field lines as it propagates outward from the point charge. So these are E field lines. Normally, when they're not moving, this is what they're missing in this picture. So normally, Q, if it's static, it's like this, right? And then, but here it's accelerating. So instead of just being like lines that go outwards in every direction, it's doing this crazy stuff. It's bending because it's like acceleration. So these lines are doing all of this kind of squiggliness in response to this acceleration, right? They're doing this, they're affected by this charge accelerating, and that causes, so this is Q, these are the E field lines. So at time equals 0 before it starts accelerating, and then some time equals t. It's accelerating, it changes the E field lines in such a way that, and they still all come back to the source. So they're still all kind of diverted back. But you can see here, that's definitely way different than the electric field lines if it wasn't accelerating. So that's the picture that we want to emphasize here. Look at that squiggliness. That's the kink in the lines of the E field as it propagates. And it would be too complicated if we drew the magnetic fields as well, but they're there. And they produce a different type of disturbance and a different kind of radiation as well. Okay, so the electric field lines of a point charge oscillating in simple harmonic motion seen at 5 instants during an oscillation period t. So what's happening here is the charge is doing something like, say it's a charge in a long wire or something, and say this is hooked up to an AC source somehow, and it completes a circuit. So we've got a source of AC voltage, and what happens is this charge gets accelerated by this AC voltage, and it's similar to a charge on it's similar to a mass on a spring where it's completing simple harmonic motion. So every so many cycles, it comes back to the place where it started, and then it goes again. That's what's going on in this picture here. It comes back to the place it started, and it goes all over again. So that's what this is expressing, the simple harmonic motion of an accelerated charge. It's constantly accelerating, and it's emitting radiation all the way, all along. Okay, electromagnetic waves with macroscopic wavelengths were first produced in the laboratory by Heinrich Hertz. And as a source of waves, he used charges oscillating in LC circuits. So there you go. Those LC circuits were the first thing they actually used to produce these waves. And he detected the electromagnetic waves with other circuits tuned to the same frequency. He also produced standing waves and measured the distance between adjacent nodes. Okay? So knowing the resonant frequency of the circuits, he then found the speed of the waves from the wavelength frequency relationship V equals lambda f. And he established their speed was the same as that of light. And this verified Maxwell's theoretical prediction directly. So by producing these light waves and using properties of circuits, he was able to confirm Maxwell's predictions that the speed that light travels is the speed of light, that these electromagnetic disturbances do travel that way, and that it is light. So Macroni and some other people made radios as a response to this, and in a radio transmitter, electric charges are made to oscillate along the length of a conducting antenna, producing oscillating field disturbances. So they go up and down the antenna. Since many charges oscillate together in the antenna, the disturbances are much stronger than those of a single oscillating charge and can be detected at a much greater distance. In a radio receiver, the antenna is also a conductor. So this is how an antenna works and how radio works, essentially. The fields of the wave emanating from a distant transmitter exert forces on free charges within the receiver antenna, producing an oscillating current that is detected and amplified by the receiver circuitry. So in your classic radio, you have charges that are free to move, and they actually respond to the signal of light that's being produced by your source. It could be a satellite, it could be a radio tower. That's what those radio towers do. They produce this light, like AM radio towers. They produce these AM radio waves, and then your AM radio receiver responds to those waves and oscillates in such a way that the signal is recognizable to the human ear as information. And it gets amplified by the amplifier so that you can hear it distinctly. And the amplifier obviously converts the electronic signal into an acoustic signal that you can detect with your ears. So the light is essentially the sound is sent as in a form of information as light, which is then converted back into sound. There's the electromagnetic spectrum. So we have a huge range of wavelengths. What you'll see here is that there's an inverse relationship between wavelength and frequency. The speed of light is always equal to lambda f. So c equals lambda f. But a lot of times you'll see mu used in place of f. This is frequency. Okay? So lambda then is equal to c over frequency, and frequency is then equal to c over lambda. So they're inversely related. So if something has a higher frequency, it has a bigger or smaller wavelength. Bigger or smaller? Higher frequency. Which one? Smaller, right. So the most highest frequency gamma rays that we can think of have tiny, tiny wavelengths. And the wavelength does change the behavior fundamentally of the photon. The photon acts more like a particle when it has a smaller wavelength because it can't bend around things as much. It just collides with things and transmits momentum more like an actual particle that has mass, even though it doesn't. And I want to emphasize that none of this light here has any kind of mass, so to speak, at all. It's all massless. So the frequencies and wavelengths found in nature extend over this massive range. So there's the visible range that our eyes have evolved to detect. This is the peak emission of light from the sun. We have evolved in direct response to the sun. If we were orbiting around a different star on a different planetary system, our eyes would be adjusted differently, and we would be adjusted to a different spectrum. We've evolved because this is the peak radiation range that the sun emits, just to repeat. That's a very interesting fact. Okay, ordinary white light includes all visible wavelengths, red, green, and blue. Yellow's not a primary color, actually. It's red, green, and blue, actually. So, using special sources or filters, we can select a narrow band of wavelengths within a range of a few nanometers. Such light is approximately monochromatic light. An absolutely monochromatic light with only a single wavelength is an unattainable idealization. When we say monochromatic light, we usually mean a small band of wavelengths. So basically, light from a laser is much more close to being monochromatic than light is in any other way. But it's never perfectly the same exactly. There's always a slight variance. Okay. So there's other animals besides us that can see different wavelengths, like birds and I think butterflies can see 5 colors, something like that. It depends. That's kind of an interesting fact. Invisible forms of radiation are no less important than visible light. Our system of global communication depends on the radio waves, which are much larger waves. Like, they can be meters to kilometers. Huge range. And radio waves are very important for our observations of space, because things that emit radio waves can be seen for a very long distance, because these really large radio waves, they don't just get broken up and destroyed when they interact with, like, say, atmospheres of Earth or some other object. They just bend around them so we can detect them more easily. So depending upon the type of radiation, that determines, like, the type of satellite that you'll see. You'll see those huge ones with giant dishes. A lot of those are meant to detect, like, the really large wavelength radio waves. And then we use microwaves for cooking and also for communication. So when you put your cell phone up to your head, you microwave your head a little bit, cook your brain a little bit. Okay. And for weather radar, many cameras have a device that emits a beam of infrared radiation. Infrared is also the range that our bodies emit light continuously in. So you can see a person's radiation emission on an infrared camera. Okay, and then gamma rays are used to destroy cancer cells. They can also give you cancer as well. So they destroy cancer cells by killing, and I want to explain this because people get confused. How can you, when somebody's got cancer and you shoot them up with gamma rays, aren't you just giving them more cancer? No, it's not that simple. So this is what it is. So gamma rays kill cells in two different ways. They really kill cells by just zapping them. Like if you hit a cell with like a really high energy gamma ray, it's going to just kill that cell. Like it's just dead. That's what they use. It basically like just destroys it, just obliterates it into pieces. That's what they do to the cancer cells when they shoot gamma rays at a tumor site. And it's much more precise of a targeting system than using like a scalpel. And also it turns out that like when you operate on somebody with a cancer, if you miss a spot of the tumor, it's like the operation didn't even make any progress because the tumor just grows right back. So the gamma rays are more effective at targeting and hitting that cancer site, especially in like difficult, like complex ways that the tumor will grow. But how does gamma rays give you cancer? What happens is certain high energy radiation, and it's not just gamma rays, it's also UV light, so you can get skin cancer from UV light. What happens is the light comes in and it hits one of your cells, and it doesn't kill your cell, but it knocks some electrons off of your DNA nucleus. In the chromosome, it does some kind of damage to like a couple of electrons in your chromosome and essentially affects the DNA because you've got these chromosomes that are all wrapped up in your cell nucleus. And so you damage some of the electrons, knock them off, ionize them in your cell nucleus, and then what happens is the cell doesn't die, but it just gets genetically screwed up. And then it doesn't work properly anymore, and it starts becoming a cancer cell. So that's how it gives you cancer. It's a different mechanism. But anyway, that's sort of an interesting fact about high energy radiation that became a real problem in the nuclear era because they didn't know about this. So all the scientists, including Hertz and a lot of these early scientists, Fermi, they got exposed to this dangerous radiation and they died of cancer like in their 50s, a lot of them. Okay, so the mathematical description of classical light. When we have a large number of photons, we can treat these excitations of the electromagnetic field as if they were really plane waves with alternating E and B fields. The reality is more complicated than this, as I said before, but in reality, the plane waves are continuous, whereas photons are actually discrete quantized excitations. But if we have a lot of them, a large number, there's so many of them that it looks as if they're just a continuous wave. So that's why this treatment works for many applications. The classical description of light we use works well for many practical applications. So we're going to focus on the classical description. And it is always true that light does consist of alternating electric and magnetic fields, and that's an important thing quantum mechanically as well. So this is everybody who does physics still has to know this in order to extend the model of light into the future. So if you're a physics major, you still have to know this when you start going about quantizing things. And actually, this is an important lesson because essentially what you have to do is you have to know the classical description of a system to figure out how to even quantize it to begin with and make it quantum mechanical. So we always have to start with the classical understanding anyway. So we're ready to develop the basic ideas of electromagnetic waves and the relationship to the principles of electromagnetism. We'll postulate a simple field configuration that has wave-like behavior. We'll assume an electric field E that has only a Y component and a magnetic field B with only a Z component. So we're going to simplify the direction of propagation so that the E field is always in the Y and the B field is always in the Z. We can always, for any wave traveling in some general direction, we can always just do a rotation and reorient our axes. So this description is complete, right? We don't have to make this more complicated by making the wave go in some random direction. We can always rotate our axes to this. So this description is not just some special case. It's the full description. let's see. We'll assume both fields move together in the x direction with a speed c that's initially unknown. And as we go along, it will become clear why we choose the electric and magnetic field to be perpendicular to the direction of propagation, because that's how they're actually oriented when these things travel. And we'll test whether these fields are physically possible by asking whether they're consistent with Maxwell's equations, which of course they are. Otherwise it wouldn't be in this book. Particularly Ampere's law and Faraday's law. And then, let's see. Okay, so that's just a summary of what we're going to do. So we're going to use an x, y, z coordinate system. And we imagine that all space is divided into two regions by a plane perpendicular to the x-axis. At every point to the left of this plane, there is a uniform electric field in the y direction and a uniform magnetic field in the z direction. So, furthermore, we're going to suppose that the boundary plane, which we call the wavefront, moves to the right. Okay, so enough of the talk, and let's actually draw this thing out a little bit. So, I'm going to draw this out on the board in some colored chalk. You're welcome to do this as well in your notebook, just following along with the... Okay. So, we've got our axes here. Now, in every place, the E and B field are perpendicular to each other. So we have just all of these little we could almost think of them as like mini coordinate systems, where we have E field going this way always at different points. And then draw a little arrow. It's a vector field. And then our B field is always perpendicular to it. These are just several of an infinite number of fields, E and B fields. And what you'll notice is that these form a plane. So as this is traveling, it's traveling this way, right? It forms a plane. And the plane of this is what's shown here. So we have this little plane here. See how I'm going to do this, okay? It's just going like this. A plane. And the E and B field are in the plane of this. And there's a vector pointing out from the surface of this plane. It's in the same direction as the area vector, dA, perpendicular to the plane of this. And that's the speed of light, c. So this thing propagates like a plane going out that way. And the electric and magnetic fields are uniform behind the advancing wavefront and zero in front of it. So there's nothing in front though. So once we get, so this is actually wrong. So let me erase this. There is no E and B field in front of it. But once it's gone, once it's passed by, there is an E and a B field behind it. But this is in the plane and this is behind it. Nothing is in front. E and B are both zero until this thing passes in front of it. Okay, so then let's talk. So the E and B fields travel to the right into previously field-free regions with a definite speed of the speed of light. This is a rudimentary electromagnetic wave, such a wave in which at any instant the fields are uniform over any plane perpendicular to the direction of propagation is called a plane wave. Okay, so that's we won't worry about how we actually produce this field configuration because it can be complicated. We're just going to ask whether it's consistent with the laws of electromagnetism. So what does Maxwell's equations have to say about E and B fields doing something like this? We've never used Maxwell's equations for just the free fields themselves. We've always considered whether a case where we have a charge producing an E or a B field, or maybe a charge with velocity producing an E or a B field. But we've never before had a situation where we have fields for the sake of themselves. That's a very important concept because, I'm just going to say this once, that's exactly how modern physics looks at it. In modern physics, you have all the fields for the sake of themselves existing. And then when you produce certain types of energetic reactions, stuff comes out of those fields that are there to begin with. So this idea of there being like fields for the sake of themselves that are excited out of the vacuum, it's not here, because that's what we're doing here is a little different. Here we're just talking about a plane, but you could think of it as like that plane is exciting an electric and a magnetic field into existence. It's a little bit different of a model, but not all that different from how modern physics views it. Anyway, let's see what Maxwell's equations have to say. So first, we're going to verify that our wave satisfies the first and second equations. Gauss's law, which and for electric and magnetic fields. So we're going to take a Gaussian surface, a rectangular box with sides parallel to the xy, xz, and yz coordinate planes. Okay, so we have a picture of that here. So let's surround this, let's make some more of these fields, and let's turn this wave train into a Gaussian box surrounding it, a Gaussian surface. So we can choose whatever surface we want. It doesn't have to be a sphere. It can be any surface at all, and it should obey Gauss's law if we're doing it correctly. So we'll do that. So we'll make this into a box here. Okay. Down like that. Okay. Can everybody make sense of this drawing? I'm going to try to make this a little bit thicker of a line here so we can see what we're doing. Okay. Okay, so all my charge, or not my charge, all my field is surrounded by this Gaussian surface. Okay. So the electric field is the same on the top and bottom sides of the Gaussian surface. So the total flux through the surface is 0. So can everybody see how that's true there? The flux is the same on the top and bottom sides of the Gaussian surface. Okay. All right, good. So the magnetic field is the same on the left and right sides of the Gaussian surface. So the total magnetic flux through the surface is 0 as well. So there's only one little thing that is kind of wrong about this drawing, which is that, like, if we're going to interpret these words the way that they've said it, they've said that the electric field is the same on the top and bottom sides. So really, it should be kind of something like this, right? Because we've got E fields top and bottom, and then we've got, I don't know why I wrote an E there. These are B fields. B fields left and right. So let's make this more precise, and let's do that. So that's a better drawing than the book, because that's what the book is saying. So why haven't they done that? And that's correct. So there we go. So there's actually an E field top and bottom, B field left and right, same on both sides. So now the flux is 0. We can see that, right? Okay, great. So let's go back to the paragraph here and see what else we have. So the box encloses no electric or magnetic charge. The total electric flux and magnetic flux through the box are both a 0, even if part of the box in the region is in the region where E and B are 0. This would not be the case if E or B had an X component parallel to the direction of propagation. If the wavefront were inside the box, there would be a flux through the left-hand side of the box at X equals 0, but not the right-hand side. Thus, to satisfy Maxwell's first and second equations, the electric and magnetic fields must be perpendicular to the direction of propagation. So the wave must be transverse. So we have, in order to obey Maxwell's equations, the electric and magnetic fields have to be perpendicular to the direction of motion. They stay perpendicular and the field goes that way. And that's what they're saying there. If they're angled at some different way, like this, then they're not obeying Maxwell's equations. They have to be like this, and then they're obeying Maxwell's equations. Okay. So, the next of Maxwell's equations, so that took care of the first two. The next we consider is Faraday's law. So we've got this E dot dl is equal to the change of the magnetic flux through a surface with respect to time, minus that change. So we remember Faraday's law there. Okay? So, to test whether our wave satisfies Faraday's law, we apply this law to a rectangle of EFGH that is parallel to the XY plane, as shown in figure 32.7b. A cross section in the XY plane, this rectangle has a height A and a width delta X. Okay, so here we go. We have our height A and a width delta X. So we're going to apply this. We're going to take this surface and we're going to erase it now. And we're going to go back to our coordinate representation of our E and B field. So we're going to keep the E and B fields, but we're just getting rid of our Gaussian surface, which is, it's an imaginary surface anyway, so we can keep it or erase it as much as we want to. For now, we're going to erase it. So we're going to erase this, clean this up a little bit, and we're going to start all over again. And we're going to try our analysis for Maxwell's third equation. Okay, so we've got these planes that correspond to these wave fronts. And so we've got three of them here. So we'll just do three different planes. They're like slices of sheets of paper here and outwards, here and here. Okay, not very good. Got that perspective all wrong. Okay, let me redraw that. Okay. So the perspective should be like this, this, and this, and this, and this, there. Okay. Go further down and up. Okay, further down. And let's see here, and up. Okay. Better. Slightly better. Still could be even better, actually. Okay. There's this sheet here, sheet there. Okay. Now I can see why my class didn't teach this. It's hard to draw. Okay. So there you go. There's our three sheets. Terrible, terrible drawing, but you get the right idea. Okay, so let's do it in a different color so we can make some sense of this here. Okay, so I'm going to do this, and I'm going to make this GHFE. So these are the sides of my box that corresponds to my wave fronts. Okay, so to test whether our wave satisfies Faraday's law, we apply this law to a rectangle, EFGH, that is parallel to the XY plane as shown. And then a cross section in the XY plane, this rectangle has a height of A. So this total height of this rectangle is A here. That's this distance. Height of A, label it A there, and then it has a width of delta X. So our width here is delta X. At the same time, the wavefront has progressed part way through the rectangle, and E is 0 along the side EF. So this rectangle is past the wavefront, so there's no E field here because it's past this last wavefront. So E and B are both 0. Okay? So in applying Faraday's law, we take the vector area dA of the rectangle EFGH to be in the plus Z direction. So the Z direction is this way. This is Z. Z is like this. And so we take the vector area dA to be in that direction. Can everybody see how this dA coming out of this rectangle surface is Z? Great. So that's Z. With this choice, the right-hand rule requires that we integrate EDL counterclockwise around the rectangle. At every point on the side EF, E is 0. So the E field is 0 on the side EF. So E field has no component on this side here, because, as you can see here, there's the E field, there's side EF. So there's no component along this side because it's outside of the wavefront. There's no field there yet. It hasn't gotten there yet. So at every point on the sides FG and HE, so this side and this side, E is either 0 or perpendicular to DL. Only side GH contributes to the integral. So the E field has no dot product along this side or this side because it's perpendicular to it. So the dot product of the E field component with this side and this side is 0. But this side does contribute. So this is the side that where I get a contribution to this integral. So the total sum, the total of this integral, E dot DL, is minus EA, where DL is A, the length of this. That's the piece that contributes to my integral and gives me my contribution there. Does that make sense? Okay, great. So we've taken the field, we've integrated it, and found its value along this integration point. Okay. On this side, E and DL are opposite, and we find that the left-hand side is non-zero, so that's where the negative sign comes from. Okay. So then we have this other situation here where we've got, in the time dt, the magnetic flux through the rectangle in the xy plane increases by an amount d phi b. This increase equals the flux through the shaded rectangle with area AC dt. That is, d phi b is equal to BAC dt. Thus, d phi b by dt equals BAC. Okay, I'm going to go over that a little bit more now. I'm not going to just run through that. That's a little bit of math there. So, to satisfy Faraday's law, there must be a component of B in the z direction, perpendicular to E. So there can be a non-zero magnetic flux through the rectangle EFGH and a non-zero derivative, because we have a situation where there's a change with respect to time. The B field can change through one of these surfaces. There was no B field here at one time, and then suddenly there is. So that's a flux. That's a change, d phi b by dt. And in our wave, B has only a z component. You can see that here. It goes along z. Same direction as the area vector, z, plus and minus z. We've assumed that this component is in the positive z direction. Let's see whether this assumption is consistent with Faraday's law. During a time interval dt, the wavefront traveling at speed c moves a distance to the right. And this increase, so it increases by d phi b is equal to BAC dt. So the rate of change of magnetic flux then is given by this. d phi b by dt equals BAC. Okay, so the change in flux with respect to time is equal to the B field times AC, because the area sweeping out, the sweeping out of the area AC dt out of the rectangle is that. So you can see that from this picture here. Okay. So we've got this C dt. That's the width of this rectangle where the change happens. The change occurs between these wavefronts. From one wavefront to the next is C dt. That's the distance there. This has units of distance. So speed of light is meters per second. So C is meters per second. Time dt is seconds. These cancel. This has units of meters. So C dt is the distance at which where the flux is changing. So this increase equals the flux through the shaded rectangle with area AC dt. The area of the rectangle is this length times its width, AC dt. Okay. So we have d phi b equals b AC dt. Thus, so d phi b equals AC dt. So then we have it should be BAC dt. Yeah, magnetic field as well. So then we take the change with respect to time of that, and then d phi b by dt. My dt's just cancel. And so then I have d phi b by dt equals BAC. Okay. Actually, one more time I'm going to look at this little picture here. So there's another cutaway view of it. So we rotate, we just look at the axes here. This is my X and Y axes for this picture here. I've got this path that I'm going along here. You can see here the width of this rectangle is CDT times this A. Okay? So we have that CDT is the area. So we have ACDT is the area of my rectangle, and then B changing through it. So we have BACDT, and then we take the change with respect to time. The dt cancels. This is like an integral differential bit, by the way. So this is a differential amount dt. I can take as small of a piece as I want, so I have a differential amount of change here. So this is really a way of doing a differential equation. Maybe you haven't had differential equations yet, but that's the reasoning here, is that we can make this bit as small as we want, and then we look at the differential change of flux, and then once we have the differential, it's just merely a matter of saying, okay, if this is d phi b, then d phi b by dt is d phi b by dt. So we just simply divide this differential out, and we have BAC as our result. Okay, so that's how they come about and get that result. And remember, E and B are 0 here, but they're not 0 here, so this is where we have the flux occurring. Okay, so we have it obeying Faraday's law and Ampere's law. So now we can substitute into Faraday's law, and we get minus EA equals minus BAC. So we took the two results, this one and this one, and we can relate them to each other through Faraday's law. And so we get minus EA equals BAC. See where we got these two from? So we have minus EA equals BAC. Okay? And then it's minus BAC, actually, because there's a negative sign that gets introduced into that. So then we can cancel our A's, and we have this interesting relationship, E equals BC. So then the speed of light, C, is equal to the ratio of E over B. It's pretty interesting. So the electric field magnitude, and we should emphasize here that we're looking at magnitudes, not just like the value at any point here. So the electric field magnitude. And why is it a magnitude? Because we did this integral. When we took this integral of E along this path, this turned into a magnitude here. So this is a magnitude, and this is a magnitude as well. This turned into a magnitude. Okay. That's why that's a magnitude. All right. So, our wave is consistent with Faraday's law only if the wave speed and magnitudes of E and B are related. If we assume that B was in the negative z direction, there would have been an additional minus sign. Since E, C, and B are all positive magnitudes, no solution would then have been possible. Furthermore, any component of B in the y direction would not contribute to the changing magnetic flux. So we have that Maxwell's equations are only obeyed if we have this very special set of constraints for this wave disturbance. So we can do a similar calculation with Ampere's law, and there's no conduction current, so the IC is equal to 0. And then Ampere's law simplifies into this form, and then you can check whether it's consistent with Ampere's law. You move the rectangle so that it lies in the XZ plane, and again look at the situation where there's a time when the wavefront has traveled partway through the rectangle. We take the vector dA in the y direction, and so the right-hand rule requires we integrate BDL counterclockwise, and you get this result. So doing the same process, we take the same little bit of rectangle here, and we go around this way, and we look at B. We look at the B field. So applying Ampere's law, we have in a time dt the electric flux through the rectangle in the xz plane increases by an amount d phi e. This increase equals the flux through the shaded rectangle with area AC dt. So there's a flux through this rectangle with area AC dt, just like we did in the last result, and this gives us EAC dt. Thus d phi e by dt equals EAC. Just like before we did it with the B field, now we're doing it with the E field. Same exact result. So the left-hand side of 32.5 is non-zero. The right-hand side must be non-zero as well. Thus, E must have a y component perpendicular to B so that the electric flux through the rectangle and the time derivative can be non-zero. Just as we inferred from Faraday's law, we conclude that the E and B must be mutually perpendicular. So this just tells us the result we already knew, that things are perpendicular. Okay, so there we go. d phi E by dt is equal to EAC. Okay, so there we have all of the things put together. Then we can substitute into Ampere's law, and we get another interesting relationship between the magnetic field and electric field amplitude. We get that B, the magnitude of the B field, is equal to E naught mu naught C E. So that tells us how the B field and E field magnitudes are related to the permittivity and permeability of free space along with the speed of light, the propagation velocity. So there we go. Okay, then we have a result for the speed of light being equal to 1 over the root of these permittivity and permeabilities, which kind of makes sense, right? Because if like the simplest way to think about permittivity and permeability is the ability to support in electric and magnetic fields, respectively, then how much it's supported is going to determine how fast it goes. Think of it as like the permittivity and permeability. It's almost like, think of them as like maybe like friction coefficients or something, where it's like you slow it down by a certain amount depending upon making it larger or smaller, makes the speed slow or get faster if you make it smaller. It's the same kind of rough idea here. Although maybe it's a better way to think of it is in terms of like a viscosity, because it flows more than it does move, right? It's more, a field is better explained by fluid mechanics than by regular mechanics, if anything. But still, it's sort of a rough way to think about it. It's like, okay, it's basically like the values, these coefficients in free space, these permittivities and permeabilities, they determine how fast this thing can go by how much it supports the propagation of the fields in free space. Okay, let's take a 10-minute break and then we'll come back. Okay, I think pretty much everybody's back. During the break, somebody asked me a question about why I was drawing it top and bottom for the E and B fields rather than like it is in the book. The reason I did it that way is because in the book it talks about the flux through here and here, and it says its net flux is 0 in both cases. But I wanted to illustrate the idea that there's fluxes possible through both surfaces. Obviously, if we just had this piece here, then there's only a flux at all through the top, right? E can only go through the top, but the same amount enters as leaves, so it's still 0, and then there is no flux on the bottom. However, we can also consider negative components, right? E fields can be negative, so we can consider negative E and negative B components, negative components, and then we have flux going through the bottom, but the flux through the bottom is also 0. It goes through the surface and then leaves the same amount. Same thing for B field. So just wanted to clarify, that's why I drew it that way, because I wanted to connect what it's saying, that technically fluxes through both surfaces are possible, but they will still be 0. Or if we just have here, there's only fluxes going through two surfaces, but it's still 0. And then there's no flux at all through the surfaces in either of these two cases. Okay, make sense? All right, great. So let's jump into the next part of this interesting result. So we have this fascinating result that our assumed wave obeys Ampere's law only if B, C, and E are related, as in this way. So we have these cool values for the permeativity and permeability of free space giving us the speed of light. And then we can plug in values to these, and actually we find that the speed of light is 2.998 times 10 to the 8th meters per second. So we don't even have to do any fancy measurements to get the speed of light. However, the speed of light has been measured by Michelson and Morley, and they did it around the turn of the last century, and they found that it was the same no matter which direction they looked at, which would emphasize that there is no ether, that it just travels at a constant. But Einstein was not even aware of this experiment, apparently, when he did his theoretical calculations with it. So Einstein, his thing was the magnetism law doesn't obey Newton's law, because if the velocity, if the force depends on the velocity, then it's such the case that Newton's third law will not always be obeyed. But if you make the speed of light constant, you can change it and make Newton's third law respected. And I'll probably try to go over that next week after we come back when I talk about relativity. But anyway, that's just a little tangent about how they actually figured out that the speed of light was a constant. It was actually done theoretically before it was measured experimentally, but the experimental measurements confirmed it. So our wave is consistent with Maxwell's equations, provided that the wavefronts move with the speed given by the speed of light, and that they are propagating perpendicular to the direction of propagation. So this gives us another right-hand rule for the direction that C goes in, E cross B. So we have another cross product for our vector calculus to enjoy. The wave is transverse. Both E and B are perpendicular to the direction of propagation of the wave. The electric and magnetic fields are also perpendicular. The direction of propagation is in the direction of the vector product, E cross B. So you point your thumb of your right hand in the wave's direction of propagation. Imagine rotating the V field 90 degrees in the sense your fingers curl. That's the direction of the B field. It's not that important, honestly. I mean, nobody really uses the right-hand rule for this stuff, but it's kind of interesting. Okay, so we can generalize this. Suppose we have several wavefronts in the form of parallel planes perpendicular to the x-axis, and they're moving to the right with speed c. If E and B are in the same at all points within a single region between the two planes, but the fields differ from region to region, the overall wave is a plane wave, but one in which the fields vary in steps along the x-axis. Such a wave could be constructed by superimposing several of the simple step waves we discussed. It's possible because the E and B fields obey the superposition principle in waves, just as in static situations. So when two waves are superposed, the total E field at each point is the vector sum of the E fields and the B fields. We can extend the above development to show that a wave with fields that vary in steps is also consistent with Ampere's and Faraday's laws, provided that all the wavefronts move with the speed c. So what they're saying is that we don't just have to consider planes that have like the same magnitude. We can also have planes that have where E has different magnitudes and still make it work. So this could be like B in this region, and this could be like E, and then this could be like 2E, and then this could be like maybe 2B. And their laws are still respected because of the principle of linear superposition. So the field doesn't necessarily have to be perfectly uniform as a plane propagation. There can be some variance and it still works. They also have this polarization property, which is kind of related to spin. And we're not going to talk about that too much. That's going to be something that we don't have time to cover. Okay, so we talked about mechanical waves. Did we talk about mechanical waves? Did you ever talk about mechanical waves in your other physics class? Yes or no? Yes, you did. Okay. So you know the basic wave equation. So it turns out that the displacement at any point in a mechanical wave must satisfy this second order partial differential equation. The second derivative with respect to my function y of x and t with respect to x is equal to 1 over the velocity squared times the second derivative of y with respect to t. So this is our wave equation, and v is the propagation of the wave. We can do this for an electromagnetic wave. We can consider a plane wave and assume that at each instant EY and BZ are uniform over any plane perpendicular to the x-axis of propagation. So I don't really have time to go into depth about this derivation, but I'm going to keep it in the slides because it's very nice to see. And I do recommend you going over it. You might get a chance to see it from Charles in discussion because it is a very cool derivation, but it would take the rest of this class for me to do justice to it. And I'm not going to put any specific exam questions where you have to derive the wave equation. So I think a better use of class time, since we're running out of time, would be to sort of just make a passing talk about this without doing a full derivation on the board. But just in passing, you can see here that we can use we can use Faraday's law and apply it to a rectangle lying parallel to the xy plane, and we let the left end of GH of the rectangle be at position x, and we let the right end, EF, be at position x plus delta x. At time t, the values of EY on these two sides are given by this, respectively. When we apply Faraday's law to this rectangle, we find that instead of E dot dl equals minus EA, we have E dot dl is equal to this result. So here we have a difference here. So what did we do? We looked at these two different points here, and we apply Faraday's law to a rectangle with height A and width delta x parallel to the xy plane. So here we have delta x, and we have A, height A here, and then we apply it, Faraday's law, to it, and we have a side view of this. This gives us that one result, and then we find the magnetic flux through this rectangle. Assume delta x is small enough that BZ is nearly uniform over the rectangle. In this case, phi b is equal to BZA, so that's equal to BZA delta x. And so then d phi b by dt is equal to dBz by dt A delta x. And then we have these two little differential segments. So we can use partial derivatives. This is a partial differential equation. This is mathematically where physics goes, by the way. If you want to continue studying physics, this is the kind of stuff that you get to do later on. You get to start taking laws, like little geometrical laws, and then you divide things up into differentials, and you form new differential equations from them. This is in essence all there really is to physics. This same process, okay? All these geometrical relationships, they're all used to construct differential equations. Faraday's law and Ampere's law are just tools that we use to construct the differential equations to describe the behavior of the fields. So here we have these two differentials. So you see we have the field EY at position x plus delta x t, and position y at just position x. So here we have, there's no differential here, and here it is at a little differential bit of displacement. And then we have, that's equal to minus dBz by dt a delta x. Same thing for bz. We have ey then, oh yeah, the a just drops out is all they're saying there. And then we divide by delta x. So ey, so dey, can you see how this is a differential of ey? It's a differential of ey because we have a little bit of change of ey as it changes position with respect to a change in position, and that's equal to dBz by dt. Okay, so we imagine shrinking the rectangle down to a sliver so that delta x approaches 0. That's calculus. That's the part where we make the infinitesimal bit tiny. It's infinitely small. That's pure calculus. When we take the limit of this as delta x goes to 0, we get this equation. So now we just have a full-on differential equation. It shows that there is a time-varying component of the magnetic field, and there must also be a component of Ey of electric field that varies with x. So we put this relationship away for now, but then you can see here that we can apply Ampere's law to this integral, and we get this result. Okay, so again, we use these differential equations and this geometry to get this result for the change in flux of electric field with respect to time. And notice that that's equal to the change in electric field along the y-axis with respect to time times this area a delta x. Now we can substitute this into Ampere's law, and we get that this interesting result that these two differential bits of change of z, B field in the z direction, they equate to this permittivity and permeability times the change in the E field with respect to time times the area. And then we divide both sides and take the limit, and then finally we have a final step. We take the partial derivatives of both sides of that last equation with respect to time. So we had our equation, and we take this derivative again with respect to time, and then we get two second-order partial differential equations. The second derivative with respect to Ey with respect to position is equal to the second derivative of B with respect to both position and time. Mixed partials on the bottom. Nasty. Mixed partials. Have you ever seen it before? Maybe. Probably not. This might be your first time seeing mixed partial derivatives. They're very common in physics. Second order partial differential equation has mixed partials all the time. Anyway, we do the same thing for z, bz, and we have mixed partials on this side, and we have our permittivity and permeability. They're very symmetric looking, but they're not perfectly symmetric. Interesting thing that this asymmetry comes about from, again, the fact that E and B fields, there are no magnetic monopoles. That all kind of traces back to that. Okay, combining these two equations to eliminate for BZ, we get our wave equation. So we have our wave equation. It turned into a wave equation because we were able to equate both of this. We were able to equate this side with this side and this side with this. These two sides are the same, so then these two must be the same. And these two cross-diagonal pieces, these are our wave equation here. That's our wave equation. So there we go. And it has the same form of the general wave equation. We found this before, and so we know that we have our wave equation. Okay, sinusoidal electromagnetic waves are directly analogous to mechanical waves on a string, which we studied before. So the wave travels along the string and it keeps its shape, travels. It's not a pressure wave. It's not a pressure wave. It's a sinusoidal wave. So, some sinusoidal electromagnetic waves are plane waves. They share with the waves described in section 32.2 the property that at any instant the fields are uniform over any plane, perpendicular, just like here. Okay? Those are the plane ones. The entire pattern travels in the direction with speed c. Other ones are not plane waves. These are not plane waves. When I have an oscillating charge that's being accelerated, it's not producing plane waves. However, as the waves are produced, they spread out, okay? They spread out. And as the wave spreads with time, the wave fronts, they sort of become perpendicular. And so in the limit that we have a large distance, that we're a large distance away from a source of radiation, the waves start coming to us more and more perpendicularly. Just like the surface of the Earth looks flat because we're at such a far distance away from the center. And so it's a very rounded surface. This is like a spherical rounded surface that becomes flattened as you go further out. And because it just continues to spread out with volume as it increases and goes forwards, propagates forwards, it quickly looks like a plane wave. So that's why it's so useful to treat electromagnetic radiation as if it's a plane wave, because it quickly looks mathematically very much like a plane wave, even though it starts out never being a plane wave, essentially. So yeah, in the same way the curved surface appears flat to us. Okay. So the frequency f, the wavelength lambda, and the speed of propagation c of any periodic wave are related by the usual wavelength frequency relationship c equals lambda f. If the frequency f is 10 to the 8th hertz, typical of commercial FM radio broadcasts, the wavelength is given by this. So we always have a way to tell what the wavelength of something is by using this equation, c equals lambda f. And this shows the inverse relationship. Now we have this sinusoidal EM wave showing how it actually looks like. So this is a linearly polarized sinusoidal electromagnetic wave traveling in the x direction. The electric and magnetic fields oscillate in phase. So E and B are always this magnitude at the center, and then they oscillate up and down. So you can see the height of it changes, and they flip. So E flips over and flips periodically. So now you can see why I was drawing it both ways earlier on, because it actually does flip around when it's traveling. It doesn't just stay like that. It actually oscillates. So the electric and magnetic fields oscillate in phase. E is maximum where B is maximum, and E is 0 where B is 0. Where E is in the y direction, B is in the z direction. Where E is in the minus y direction, B is in the minus z direction. At all points, the vector product E cross B is in the direction in which the wave is propagating, x direction. So E cross B will always be this direction. Okay. And caution, in a plane wave, E and B are everywhere at points on the x-axis only, but in fact, in a sinusoidal plane wave, there are electric and magnetic fields at all points in space. Imagine a plane perpendicular to the x-axis that is parallel to the yz plane. At a particular point and time, the fields have the same values at all points in that plane. The values are different on different planes. So we can describe electromagnetic waves by means of wave functions, just as we did in section 15.3. For waves on a string, one form of the wave function for a transverse wave traveling in the plus x direction along the string is given by this. So this is just simple harmonic motion. A is equal to cosine omega t. Okay? This kx value, you can think of it as like the initial phase of it. These have the same units, right? They're the same units. So this is just omega is the oscillation and t is the time here. Okay, So we have simple harmonic motion. Y is equal to a cosine x minus omega t. It's a little different though, but basically it's essentially the same as simple harmonic motion. And y of x of t is the transverse displacement from equilibrium at time t of a point with coordinate x on the string. So we have a is the maximum displacement or amplitude of the wave. Omega is its angular frequency equal to 2 pi times the frequency, f, and k is equal to 2 pi over lambda, the wave number. So let e of y of x of t and bz of x and t represent the instantaneous values of the y component of e and the z component of b, respectively. And then we have E max and B max represent the maximum values of these fields. So then the wave functions for these waves are then given by this. And these are real waves. They're actually describing the behavior of the amplitude of the wave with respect to time. So E max changes and B max changes with respect to time, given by this phase factor here. Okay. And then we have applications from space. Plane waves, the moon, sun, planets, and stars are so distant the light we receive from them is well approximated by plane waves. So we don't have to worry about designing telescopes that treat anything other than plane waves. As the light comes and reaches us from a distant object, the light hits us essentially as a plane wave where the amplitude is uniform across and uniformly distributed. All right, keep down the talk a little bit. It's a little distracting, please. Okay. No talking, please. It's distracting. Okay. So we have our wave functions in vector form. E of x of t is equal to this j hat, E max cosine of the angle, kx minus omega t, and b given by this k hat. So j and k just represent our position vectors. Okay, the sine curves in figure 32.13 represent the fields as functions of x at time t equals 0. So E of x of t is equal to 0, and b is this. As the wave travels to the right with speed c, then, we show at any point the oscillations of E and B are in phase. Okay, so there we go. E max is equal to c times B max. These amplitude and phase relationships are also required for E of x and t and B of x and t to satisfy equations 32.12 and 32.14, which came from Faraday's law and Ampere's law respectively. Okay, so we've got our behavior with respect to time. You can see how it's changing direction, and the change in one is inducing a change in the other, but they're sort of like moving together. Okay, so we have the E and B fields of the wave traveling in the negative x direction, and then the wave functions are given for that. All right, great. So let's do an example really quick. So we've got, pull out a sheet of paper and try to work this. We've got a carbon dioxide laser. It emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. The wavelength is 10.6 micrometers in the infrared, and the E field is parallel to the z-axis, with E max is equal to 1.5 megavolts per meter. Write vector equations for E and B as functions of time and position. Okay, so we're going to have to describe a wave traveling in the negative x direction with E along the y-axis. It's a wave that's linearly polarized along the y-axis. By contrast, the wave in this example is linearly polarized along the z-axis. At points where E is in the positive z direction, B must be in the positive y direction for the vector product. E cross B to be in the negative x direction, the direction of propagation. So here we see a wave that satisfies these three requirements. You can see we've got B going along the y and negative y, and E going along the z and negative z. So there we go. So how do we write our wave functions that describe the wave? There we go. We've got E of x of t. So let me draw this out really quick. So So we've got our wave here. And then we'll do our B field here. Actually, I think I was doing E in purple. So we'll do our B field. Do negative y2. So we've got negative j, positive j, and then k and minus k. Okay? And then we've got our axes like this along the x. I can just do I hat actually, be consistent. Okay, so we start with some amplitude b and go down to negative b. Then we come back up again and do the whole process over again. Okay, there's our B field. Now our E field is going to start like this, and it's going to cross. And then how does it go? It comes like behind and goes like this. Again. There we go. So there we got our B field there. So there's our B and our E field. And then, so there's B here. And E. And then at a later time, E's going this way and B's going down. Okay, so then to describe this mathematically then, we've got our wave function here. So we've got E, and it's going to have some amplitude. So E is a function of position and time. It's going to have some amplitude E max times cosine. But it's also got a k hat direction. We can't forget our position vector there to start with. So we've got our position vector, E max, cosine, and then we've got kx plus omega t. So that describes this electric field oscillation completely. And then we've got our B field. It's also a function of x and t. And then it's going to be in the j hat direction. And then it's going to be B max times cosine kx. And it's going to be plus omega t as well. Okay, so there we go. There's our values. And then we can figure out what's the value of B max. If we know that E max is 1.5 times 10 to the 6th volts per meter, the value of B max is just divide that by the speed of light, and we get 5 times 10 to the minus third Teslas. So we get a really small value for the B field because we divide by a factor of the speed of light to get that. Okay, and then what do we know for the, so that's solved for B max. So just to emphasize here, so we know E max and B max. So we're going to plug those into this equation. So we're not done yet. We solved for E max and B max. We're going to plug those in now. So let's finish out this problem here. So I'm going to write that's equal to, so we have a k hat, and then we have a j hat for B, and then we know E max and B max. E max is 1.5 times 10 to the 6th. So we have 1.5 times 10 to the 6th volts per meter. That's the amplitude. So k hat times the amplitude times cosine of, and we're going to solve for that stuff later. And then B max is 5 times 10 to the minus third. 5 times 10 to the minus third. And that's Teslas. And then we've got our cosine of stuff inside that we're going to solve for. Now let's solve for that stuff inside. Okay, k is equal to 2 pi over lambda. We know 2 pi is just a constant. The wavelength is given to us in the problem. So we have k is equal to 2 pi divided by my wavelength, which is 10.6 times 10 to the minus 6th. So we have that. And then what does that give me for a value of k? 5.93 times 10 to the 5th radians per meter. What was it? 10 to the 5th, yeah, radians per meter. Okay, so we can plug that in for here. So we have cosine of 5.9 times 10 to the 5th, 5.9 times 10 to the 5th, radians per meter, okay? And then, so it's kx times x, and then plus omega. So we're going to have an omega there. What's omega? It's 1.78 times 10 to the 14th radians per second. How do we solve for omega? Omega, we have this formula here. Omega is equal to c times k. So we have 3 times 10 to the 8th times our k, which we solve for here. 5.9 times 10 to the 5th. So it's going to be some huge number like 10 to the 14. 1.78 times 10 to the 14. Okay. 1.78 times 10 to the 14. 0.78 times 10 to the 14th t. Okay, so now we have our full wave functions for this problem. Okay, so let's see how we're doing on time here. We still got 8 minutes actually. Okay, great. So, in a sinusoidal electromagnetic wave in a vacuum, the electric field E and magnetic field B oscillate in phase with each other, and they're always perpendicular to each other, and both are perpendicular to the direction of propagation. The magnetic field amplitude B max equals the electric field amplitude E max divided by the speed of light. So, now we can talk about EM waves in different materials. So, we're going to talk about in a dielectric, the wave speed is not the same as in a vacuum, and we denote it by V instead of the speed of light. But Faraday's law is unaltered, but in this equation, which we derive from Faraday's law, the speed c is replaced by v, and the displacement current is not given by this, it's given by this different epsilon naught. Instead of epsilon naught, it's given by the permittivity of the material. And k is a dielectric constant. So we didn't talk about too much materials and stuff, but just know that the speed of light changes in different materials, and it's always slower in a material than it is in a vacuum because of this. So this is how E and B are always related. You can see here that in a wave in a vacuum, we find that it's this. For any other material, it's given by this expression. Okay. So for most dielectrics, the relative permeability is nearly equal to unity, except for insulating ferromagnetic materials. So this gives us the index of refraction. So you know how light bends when it goes through water? We won't have time to cover that, but you've seen it before. It comes from this result, because light is a wave. It has a wave-like behavior anyway. We get that result. Okay. So we can, if we're visiting a jewelry store one evening, you hold a diamond up to the light of a sodium vapor street lamp. The heated sodium vapor emits yellow light with a frequency of 5 times 10 to the 14 hertz. Find the wavelength in vacuum and the wave speed and wavelength in diamond, for which k is equal to 5.84 and km is 1 at this frequency. And then do it for, we have another case, we have a 90 megahertz radio wave, passes from a vacuum into an insulating ferrite, a ferromagnetic material used in computer cables to suppress radio interference. Find the wavelength in vacuum and the wave speed and wavelength in the ferrite, for which k is 10 and km is 1,000. So we're going to have two cases where a light wave starts out with some wavelength and some wave speed, and it changes as it goes through the material. So let's see how we do it. So for part A, we find the value in the sodium light for a vacuum. So if it wasn't going through a diamond, it's just C over frequency. So it's given by this. It's 5.89 times 10 to the minus 7 meters, 589 nanometers. But in the diamond, there's these two values corresponding to the ferrite or the K or whatever values for diamond. So we have 5.84 and 1. So we have to divide this to get its velocity in the diamond. And we see that it's only 1.24 times 10 to the 8th. So it goes down to about half of its speed. It was 3 times 10 to the 8th, and now it's only 1.24 times 10 to the 8th. Similarly, for the wavelength, lambda is the velocity over the frequency. The frequency does not change. The wavelength does, and the speed does. So we've got 1.24 times 10 to the 8th meters per second, that's the new velocity, divided by the frequency of the light that doesn't change, and that gives us our new wavelength. So the wavelength actually changes. Does it become bigger or smaller? Let's see. It was 244. It was 589 nanometers, and now it's smaller, 244. That's kind of counterintuitive, actually. You'd think that it would get you might think that it would get larger, but no, it doesn't. It gets smaller. Okay. So then for the second case, we have a radio wave. So we have 90 megahertz. So we have our frequency, 90 times 10 to the 6 hertz. We have our speed of light giving us our wave speed. So we have our wavelength in the vacuum before it goes through the material, and it's 3.33 meters, so it's a radio wave. It's pretty big. It goes through the ferrite, and then it divides by these two values, 10 and 1,000. So it becomes 3 times 10 to the 6 meters per second. Its velocity becomes vastly slower than what it was before. Look at how much slower, by 2 orders of magnitude slower. And then the wavelength gets reduced down to only 3.33 centimeters, so now it's in the microwave range. So the speed of light in transparent materials is typically between 0.2 C and C. Our result in part A shows that it's 0.414 C, and B shows the speed of the electromagnetic waves in dense materials like ferrite can be far slower than in a vacuum. So that's very interesting. Okay, so the speed of light in a transparent medium, slower than in a vacuum. So we're going to talk about energy and momentum in electromagnetic waves, but I think in order to do that section justice, we're going to have to wait until next class because we're right at about time. Does anybody have any questions before we head out for today? Okay, great. So have a happy Thanksgiving. I'll see everybody when we get back, and we'll go over the final parts of the course. Do some really exciting stuff when we get back.